welcome. We just finished introducing ourselves, and so, but don't feel shy. There's food there.
Thank you.
Do you mind introducing yourself too?
Okay. So I just finished my master's program here at the math department, and this is my friend, and he invited me here.
Fantastic. Well, welcome. So, Luis, your network is broad. So there's chips and crackers and things there. And congratulations on finishing your master's program. What master's program was it?
The math course.
Oh, math.
So I just need to defend my thesis the 27th of July.
Oh, wow. Good luck.
Okay. So start with detection of mutation in cell development using artificial intelligence. So first of all, the background, well, since you're all in the lab, you guys pretty much know what you're doing. So this is just,
I hope.
this is just my, it's a little summary of what I think you guys are doing. Basically, research and development in muscles around the spinal cord. Inhibitors are injected into the muscles, also drivers to prevent muscle growth. So you guys give me basically images of the somites, and basically there are somites that are normal, some that are mutated, and there's different types of mutation. So basically, this is kind of images I get. So the purpose is, with the help of artificial intelligence, we're able to, well, we hope to be able to differentiate normal cells from mutated cells, or normal embryos from mutated embryos. We did embryos, just the entire thing at the beginning, because looking at each of the somites will be a little hard. Plus, it's the first time I do this, use this kind of technology. So, just as a small step, just be able to differentiate between a normal embryo and a mutated embryo. So, why is this useful? Basically, this will save tons of time just by looking at the mutations, and also, the humans are not perfect, so we tend to miss a lot of details in the picture. We tend to miss a lot of, like, you know, oh, you might say, oh, this is mutated, oh, this is not mutated, and it takes hours. Like as I heard from Julio, this takes hours to analyze, right?
It could take a while. You go through all the slices.
Okay.
Yeah.
But if you give it to the computer just like take a look at it, and boom, it's like, okay, this is mutated, this is not. So before jumping into like what I've done, first of all, I want to talk about what is artificial intelligence, what is machine learning, and what is deep learning. So artificial intelligence basically is a field of computer science that tries to use the human way of thinking towards computer science problems. So one of these fields is called machine learning, or called statistical learning. As the name says, statistical learning uses mathematics, specifically regressions, like all statistics, to make predictions. It's all about building a model and make a prediction out of it using complicated math. And a branch of it is deep learning. Deep learning focuses on, as well, uses mathematics, but uses something called artificial neural networks to do this. Basically, this is one of the biggest, I would say, branches of artificial intelligence, and this has been around since the 1940s. The only problem with being around since the 1940s is that back in the day, they did not have enough computer power to be able to do this, because even in the 70s, it became popular, but hey, we don't have our computers are not really strong to do this, right? And analysis that now would take hours, back in the day would take months or tons of money. And well, now with the help of, well, we have things like cloud computing, we can rent a computer. This is like being possible to be done, specifically because there's a lot of competition, which I'm gonna go later. And why is this a problem? So first of all, you see machine learning, and you hear things such as statistical learning, deep learning. So first question is, what is learning, right? What is learning? Like, how do we go from, okay, let's teach the computer to learn, right? First of all, you guys are scientists, and you guys learn how to see the mutations, right? After hours of training, after reading textbooks, after looking at all this, and like, you know, like after a while, after looking at enough data, reading enough textbooks, taking many classes, you're able to tell, okay, there's a mutation here, there's no mutation here, but how does all that process go through? And also, the challenge is, how do you teach a computer to do that? So my way of seeing this would be in 3 steps. So it's all about information. So the first step would be gathering information, right? So you have to gather information, you have to see it. And then the next step would be processing the information. Like something goes inside your brain that makes you process that, right? But then last step would be interpreting the information, because you need to make a sense out of the what you're seeing, where you're looking, what you're hearing, to be able to know. For example, if I ask you, I don't know, what is this? It's a water bottle, right? So this is a water bottle, but how do you know it's a water bottle? Because you're being reinforced to see that. Someone told you, okay, this is a water bottle. So you're pretty reinforced to see that. So let's say, for example, information is around us. Since we're kids, you know, we are born into this world without having any knowledge of anything. You basically see colors, you hear sounds, you have smells. But then later, you tend to make certain patterns in your brain, right? For example, you tend to link things like just water bottle, right? The words B-O-T-T-L-E to this object right here. You are able to make labels. You are able to see patterns like words, language, all of this. But all of this comes with experience, and all of this comes with some sort of like exposure to it, right? So let's make a little exercise right here. For example, so what if all of your babies, all right? All your babies, and I want to teach you to differentiate Coca-Colas and Pepsis, right? So after showing you like tons of images of cans of Coca-Colas and tons of images of cans of Pepsi, let me ask you, what's the first thing that you notice here?
Color.
Color, right? So if I was to show you, okay, there's a bunch of images, right? The first thing that you will capture will be, oh, the red cola, oh, the blue cola, right? And that will be it. But what if I want to be more precise? What if I want you guys to learn what the letters mean? I want you guys to see the brand. I want you guys to see the letters, to recognize this stuff. And just by showing you this, like, you guys won't even learn, because the most apparent trait here is just the color, right? So if I was to show you, I don't know, what is another brand that is red? Dr. Pepper, right? If I show you Dr. Pepper, you will say, oh, that's Coca-Cola, right? So you know how to read, but you know only how to see the color. So in order to fix this, a solution would be like, I show you other images, right? There's different types of Coca-Colas, and there's different colors of Pepsi cans, right? So after seeing all this, it is very likely that you guys will learn how to recognize these things, right? You'll see, oh, that's a brand, right? So after more training, you guys will stop thinking about colors, but you will start thinking about letters and the brand and the shapes of the P, the shapes of those things. So as a data scientist, we don't know how you process the information, but we can lead you towards that we know that you are getting this type of information. So basically, the more data that you have, the more precise your learning is, because like the more exposure to something, you are more able to see different features of that something that you're looking at. So the technology that we look at is called artificial neural networks. So an artificial neural network is basically as a neural network, like a normal neural network, like basically the same. It's not the same, but it's biologically inspired. So first of all, that's a neuron, and that's an artificial neuron. They both have dendrites. They both have the cell body and an axon. So theoretically, the dendrites get information. The axon processes that, the cell body processes that information, and the axon basically throws the output, right? In this terms right here, basically this is, you have your inputs, you have your activity. So what happens inside of this is basically a function. Let me use a little word here. This actually is an equation. What this equation means mathematically is 1 over 1 plus e to the negative x. Don't worry about understanding this, but what this looks like is basically a function that goes like this, jumps here. So it goes from 1 to 0. So in computer terms, a 1 means on, and a 0 means off. So what's going on is that there's certain things that will activate the neuron, there's certain things that will not activate the neuron. So kind of visualize this. These neurons are assembled in a certain way, right? So this is a really simple network that takes the inputs and has two outputs. So going back to the example of Pepsis and Coca-Colas, right? So if I was to show you a picture, so imagine that this is already trained network. Like we already trained it, we already gave it thousands and thousands of images. And so in theory, when you see something, so first of all, as I'm saying, so if I show you this, what is this again?
A remote?
A remote. So the process that goes inside your brain is that I show you an image, and some of your neurons activate, and if that activation goes through basically a last layer, and then you are able to say, oh, this is a control. But if I show you this, other neurons will activate, and you're able to say, oh, this is a water bottle. So here, for example, I throw it a Coca-Cola image, and some of these neurons will activate, and at the end, this last neuron will activate and say, oh, it's a Coca-Cola. But if I throw it a Pepsi, this is different. Basically, other neurons will activate, and at the end, you'll say, oh, this is Pepsi. Now, this all seems like magic, right? But how does something learn, right? How does this work? Because this seems just like, wow, just this is already trained. But how this works is that, well, let's go back to a little board right here. First of all, who used Excel before? Yes. So you guys use Excel. So now let's imagine that we're plotting something, right? And you get a bunch of data, and someone ever made a line in Excel before that looks like this?
Yeah.
Right? So let's imagine that this is, for example, okay, distance traveled in a car. So let's call this distance. And let's call this amount of gasoline used, right? So amount of gasoline used. So basically, you have your data. I mean, this is not going to be uniform because all the cars are different, all the motors are different, so the amount of gas that they use is different. But we can kind of make a prediction, right? So for example, the maximum here is like 8 hours, right? And here is like 1 hour. So we only have this information available. But if we want to make a prediction of how much gasoline will be used in 10 hours, right? Then we can make, based on this line, we can say, oh, okay, this much gasoline is going to be burned, right? Who's familiar with algebra here? Okay, algebra 2, algebra 1. So are you guys familiar with this equation? Y equals mb plus, no, mx plus b. mx plus b, mx plus b. Oh, okay, you guys are better than me. Okay, mx plus b, right? So m is the slope, right? M is the slope. So basically how fast this goes, and b is just basically how up and down this goes. Now, you put it in Excel and it guesses this line, right? And you're like, okay, cool, like, got it. But the process behind this is actually a little more complicated than that. So basically, the way this is done is, at the beginning, Excel will just show you an arbitrary line. This is not the best line, but we just choose a random line, right? This random line is not the one you want, right? Because this is not as good as the other one, but this is to start with, right? So first of all, what you do first is, well, you want to get the errors of this, right? So you calculate this right here minus this. So you do prediction minus actual values, right? So you get all these distances right here. All these distances. You get all these distances, you add them, and you square them, because you have to square them because this is positive, but this is negative. So when you square something, what happens?
It's positive.
Makes it positive, right? And also, when you square things, this is good because how does this look? How does this equation look like if I was to graph it? Something squared.
It'd just be like
A parabola, right?
Or,
So
yeah.
let's think that all these things that we added are gonna go to the parabola, right? So this parabola is basically telling us the error. So basically, if this is like, there's a lot of error here, right? Then this equation will be like, the point will be right here. So it would be like, okay, there's a lot of error. So I wanna go to the point of least error. This point will be the one that will be the line that will be here, that will have the least error, that will make the best prediction. But how do we get there, right? So there's something nice about x squared, that we can take the derivative. Anybody knows what the derivative is? So yes, we can take the derivative. At this point, the derivative is what? It's negative, positive?
It's
It's positive,
well,
yes.
okay.
It's positive. So since the derivative is positive there, the derivative is positive, then that means you want to get to this point, right? You're gonna go to the left. So what you do is something called gradient descent. So what you do is, this is positive, so I do minus the derivative, and I go here. Boom. Like, you guys can see that? So let's say that I do it again, but I get to be at this point here. I just jump to this point here. And I take the derivative here. Is the derivative positive or negative? It's negative, yes? Okay, it's negative. So if I do minus negative, what is that? Positive, right? That means because I want to go here. So I want to increase it. So I'll increase this. So this process is called gradient descent. So basically what I do is just I grab the input and I update it minus a value with the derivative of the function. This might seem a little complicated, but it's just basically I grab the derivative minus the derivative, and just to get to this point. Once it gets to this point, perfect. We get the best line, we get the best M, we get the best B. Yes.
And that's what Excel does?
That's what Excel does.
Okay, that's what.
That's what Excel does. Basically, what this does is, this is the core of all type of machine learning. This is the core of all type of intelligence, because what you're basically getting is like out of data, you're trying to get a prediction, an equation that will make a prediction, right? Because at the end of the day, you have your line, and you can ask things, right? For example, as I said, like you can ask how much after 20 miles, how much gasoline will it burn, right? So what this does is basically giving you more of an insight. So this is just a line, right? This is just a line. So how these things work is this way. Now, in real life, you don't have like only one input and one output. You have tons of information, like a lot of information. Say that you have two more variables. So actually, so this is how this looks. So that's what's going on. It's like being on a hill, and you want to go to the lowest point. That lowest point is basically what will give you the best prediction. That's called the cost minimum. Now, the problem with this is that later, when you have more data, say that you have two inputs of data, then you go three-dimensional, right? You go three-dimensional. And the concept is the same. Instead of using a derivative, we use something called a partial derivative. With partial derivative, anybody took out 3 here? No, okay, you did. So a partial derivative, basically, there's something called the gradient. The gradient, what this does is basically shows you, so imagine you're in a hill. What the gradient will show you is a vector or a little arrow that will point to the direction of most increase. But since you want to decrease, you go the opposite way. So basically, it's the same way as this equation. It's just like this: x minus instead of a derivative, this is just a gradient, which is the three-dimensional or four or fifth or multiple dimensions ways of defining this thing right here. So this is how it updates in multiple dimensions. And I'm going to explain why we need multiple dimensions. So this is basically how this thing is learning. It could get more complicated than that, because in this case, we're working with something called a neural network, which is basically not as simple as that. It's like, this is like real simple. You have that equation, y equals mx plus b. But the other equation that I showed you, the logistic equation, it's way different to work with. But it's pretty much the same concept. So it's more dimensions, more math. And in fact, so in this project, I used 1,500 neurons. Each of the neurons had about, let's say, 500 variables. So multiply 500 times 1,500. That's a big number.
Yeah.
That's a really big number. And that's a lot of mathematical operations being done. And those operations are pretty much those. And that's the reason why in the past they were not able to do this, because that requires a lot of computation power. But now, we have the resources, so we can do that.
So how does this vary from quantum computing?
Mm-hmm. Oh, quantum computing is something else. Quantum computing basically tries to improve the way computation is done. Quantum computing just aims to make things faster.
And what kind of algebra is used for quantum computing?
Quantum computing, so this is quantum computing is totally unrelated to this,
Okay,
but
so forget it. Maybe
yeah.
you know, it's funny because I had this conversation with Sheldon Axler, who's in the math department. He was the prior dean, and so he was very enthusiastic. He went to Google, and Google has like this top secret research center within Google. And I don't know what they call it.
Googleplex.
Is it Google? No, it's
No.
not Googleplex. It's Google. Anyways, it's a top secret.
It's called DeepMind.
Yeah, that's it. And so they have this part, it's top secret research in there. And what kind of math does Sheldon teach? It's what kind of, do you know what classes he teaches?
Mostly analysis.
Analysis and some other class.
Yes, but mostly analysis and.
Because he was super excited about his textbook. Okay, so it's
linear algebra.
linear algebra, thank you. Linear algebra. So he got invited to Google because of his linear algebra textbook. And he said it's because, you know, your initial equation from 0 to 1, that's how computing networks work, you know, 0 to 1 is.
Quantum computers can get multiple
Yes,
states,
and so and the framework is through linear algebra. And so he says Google has a quantum computer, and probably the government has a quantum computer.
It's a pseudo quantum computer, because
Yeah, because there's, I don't know, there's very few. There's very few, or I don't know where they're at. But apparently, once that's released, then all of our security systems are totally vulnerable.
Oh, wow.
Because of the speed of the computing. So right now, you know, you can put in your codes and stuff, but it would take a long time to go through and figure out, you know, your code. But I guess there's something about the linear algebra approach, because now you're not doing 0, 1.
Everything uses linear algebra. In fact, all these equations are matrices, like stuff in linear algebra.
So, but I don't know, it changes the computing power. So that's why when I saw you do equations, I was like, okay, how does that work?
They say that with quantum computing, we will actually achieve real artificial intelligence, because the computation will be done really fast. Because running this takes, I would say, half a day in a computer.
So you mean it thinks for half a day? And that's like
Well,
with
it's just going through the math.
It does those mathematical operations.
Oh, okay.
The math is laborious. And
Okay.
so I guess when you can switch over with
The quantum.
with the quantum, it just makes it so fast. So
Gotcha.
you're still going through the processing, but the processing can be a lot faster.
Okay.
Did I?
Yep. Pretty
Well, I'm a biologist.
No,
so I'm
no,
just trying.
Me too.
You know,
Me too. Okay.
but I was just like, I mean, it sounded kind of scary, you know, because it sounded as though, you know, we're right at the edge of that happening where artificial intelligence can really take us to a place that will potentially allow us to do really great things, but also make many of our security systems vulnerable.
That's why they're actually making artificial intelligence security systems. So
Right. They're smarter than.
this is like electricity now because everything's using it.
So sorry, Luis, I didn't mean to take you off.
It's fine. It's fine.
I think for me, you know, because I think, you know, we look at images all the time in our lab, for instance. We look at muscle, we look at notochord and all this. So when I'm having a hard time understanding the language of the computer or how it sees things, is, you know, I have my, you know, unconsciously, I can process this information. So if the computer deals with numbers, 0, 1s, or this calculations, how does that, I mean, how does it see an image? That, you know, I'm trying to understand how the computer or the machine is doing this.
So for example, here in this thing right here, you're inputting numbers, right? So in this case, it's 1, 2, 3, 4, and this is like the amount of gasoline that is, like, say, 5 gallons, 6 gallons. I'm just guessing numbers, right? So you input numbers. When you feed an image to the computer, in the computer, there's a bunch of pixels. And each of these pixels has a number. So this number ranges from 0 to 255. And what we do is basically with a neural network. So if we go back to this, basically what's going on here is that this, like linear algebra speaking, this is a matrix, but we turn all of this into one single row. So, one single column, right? One single column. So all of this gets stacked into one single column, and each of these things has a number. For example, if like say that we want to represent a number 2, right? So number 2 would be like this. Let's do a number I don't know, number 8. That's easier, right? So this number 8. This is black. This is black. This is right, and this is white, right? Each of this has a color. So basically, it has a number, right? So 0 for the computer means black. 255 means white. So you input those numbers to here, and it goes to the neurons. And in this case, say that you wanted to learn the number 8. So at the end, you will tell it, okay, it's a number 8, right? And doing all these operations, going to the least to the most fit prediction, it gets to guess that's number 8. So that's how we see. So basically, when you take a picture or something, it gets translated into an image. Each of the images is a number, and that goes to the neurons.
So it's always in black and white. It's not color.
Now, when there's color, that's something called RGB. So we can represent any type of color using 3 colors: red, blue, and green. Same process. These colors go from 0 to 255. For this project, as going back to this example, I turned all the images to black and white. The main reason I did that was just to avoid any mistakes. For example, like here, right? As I told you, like I don't want you to differentiate Coca-Cola and Pepsi just by the colors. I actually want you to see the features inside and the logo and the brand. So that's why I shut down the colors and I put them into black and white.
So what you're saying is that it scrambles the grid into a column. You said.
Yes.
That right there. So so each rectangle, black or white, still has a number.
Yes.
And it keeps track of it.
Yep.
And then you also mentioned this how many neural cells or neural usage?
So the neural networks I used 500.
So how do you, I mean, why
I chose 500 because
what does it mean? I mean, I don't.
What does it mean? Basically, what I did, so let me go through this process. I can explain it right now. So let's see. So what is in there? tools use, right? So first of all, I use the C-SEN microscope software, which is the one that you use to basically turn the images from, because your microscope takes the images in one format, but I need to turn it into a format that my program can read. Photoshop, because some of the images were like too large, too small, so I had to cut them a little bit, had to make some little changes there.
What format did you use? Is it TIFF or PIC? What format did you need to convert your images into?
I used
JPEG?
yeah.
JPEG, okay.
So, and then I used AWS. AWS is a cloud computing service from Amazon, because yeah, this cannot be done on my computer. That's like too weak. So I needed to rent this computer. So it's like $60 a month.
Wow. Is it cloud or?
It's cloud.
Cloud,
Yes.
right?
It's a cloud computer. It's like probably 20 or 30 times faster than my computer.
$60 a month is not bad though.
Yeah.
Is this through Google or Google?
No, I use Amazon. This is Amazon. I forgot the W, what the W meant, and service. But that's what it is.
And how do you know it's safe to put your? I mean, it's the cloud, right?
They're gonna steal our data.
It's good because many companies, like really known companies, use this service as well. This is one of the biggest ones. It's one of the most secure ones. So.
But what if a computer neuron goes bad and it shares it with somebody else? How do you
Well, I'm sure that's the whole security stuff. You had a password to get in. You have your own
it's
private.
Not, like basically, it's not really thinking for yourself. It's not like it's going bad. It's just basically just a mathematical operation. It's very much the same process as when you do Excel and get the best fit line. This is technically the same thing. Like
So it's just safe.
Exactly. It's just, as I'm saying, like if this is crazy, that means that your Excel gets crazy, but that doesn't happen, you know. So, okay, Jupyter Notebook, which is a software to basically start programming. CV2 is to read the images and translate that into numbers. And TensorFlow, actually TensorFlow was released by Google. This program has made things easier for data scientists because this, as I'm saying, this technology is pretty new. TensorFlow barely came out in 2015, so this is the newest of the newest. So
what does it do?
TensorFlow, it basically makes you build all these equations, makes you build all this matrices, all this linear algebra, without worrying much about the details. So as long as you know how it works, you can use it. There's pre-built mathematical operations that you can use. So it just basically makes things easier. I don't have to build everything from scratch. That's why this is useful. So basically, to analyze the embryo data, so what I did was separate 75% of the data for training and 25% for testing. The main goal of this is basically me training the embryo data with this. I show you an image, I show you images, and I tell you, okay, this is a control embryo. This is a mutated embryo. And I just do that for, thousands of times. And then later,
Yeah, but do you, how do you do one image at a time and you say, do you get it right?
No.
Do you initially you just throw the images?
It's like here. It's like here. It's not like you don't use one point at a time. You have to actually use many of these points at a time. So you can think of maybe throwing many images at a time. So you throw 10 images. So I do little batches of 10 images. Do 10 images. Then I get the predictions for those, and after that, do more math. That's where the training process is, right? So I do 75% and 25% for testing. The reason why testing is because I train it first. I'm like, this is normal cell, this is a mutated cell, this is normal cell. I do it for thousands of times. Then, for testing, I grab an image it has never seen before. I know that it's controlled, or I know it's mutated, and that's the whole purpose of this. Being able to work with images he has never seen before, because that's the purpose of intelligence, right? Because like, have you guys seen this bottle before? Probably not. It's a new bottle, but you know it's a bottle. So basically, that's the whole purpose of having testing data. So I resized the images from 1,000 to 3,600 to 500 times 100. I made it smaller. That's why I chose 500 neurons, because if it's 500, then 500 neurons takes take the image, right? I could have chosen more. The problem is computer power, because I chose initially 1,000, and that computer, even though it's powerful, it crashed.
Oh.
It
I
crashed.
I love that. It crashed the computer. It shows you the great resolution of our images.
So yeah, it crashed, and I could make it smaller. But if I make the image smaller, I might lose a lot of the features and make some mutations. So I thought that 500 times 500 was the perfect size, not too big, not too small. Same thing, as I said before, I turned the images to grayscale to avoid a problem about colors, because also some of the images you guys put the fluorescent light, I think, right? And basically that's an easy way of saying, okay, this is mutated, this is not. So I took out the color completely. And also it's easier because when you have images with color, you have to manage 3 numbers, right? Red, green, and blue. So if I do grayscale, I only have to manage 1 number. So that makes things faster. So yes, I use.
So a lot of our images have like,
Multiple.
you know, you got the embryo and then you have empty space, you know.
Yeah, the empty space, the black means 0.
That's 0. So
Yes.
whenever it sees signal, it gives it a 1, is that right? Or it turns it black and white?
So
or?
if it's real bright, that's a 255. So basically, I'll show you some of the images that it has. So basically, there's 3 layers with 500 neurons each, right? So basically, it goes. I send the images, goes to the first 500 neurons, then that sends it to other neurons, and that sends it to other neurons. So I built a little network there. Same thing. I chose three layers because I thought. I felt more. I don't want the computer to crash. That's a lot of mathematical operations. In fact, adding another neuron would basically make the time that it takes, well, 500 times like slower. So this was an arbitrary, like an educated guess, I would say.
When you have the data moving from neuron to neuron, is it like if and then statements? Is it like if this, then
No.
this, if this, then this?
It's just the mathematical operation that. So the equation for the activation function of the neuron basically is that one, right? This one. So what's going on here is that it's 0 and 1. So say that this goes here, then this sends a 1 here, and there's a bunch of 1s here, and this sends to another 1 here. So it's just basically active and inactive.
I see, 1, 0, 1, 0. So 0 is because it doesn't get sent to that
Exactly.
neuron. Okay.
So
And then, so you figured out 500 neurons because you had 500, because it's equating to the 500 pixels in a way, right? So then, as it's moving through the neurons, what is a one? I see that you have your equation. Is that, what's the criteria that it's just bright or not bright? Is that, or no? Or
we don't know. That's the thing. We don't know. As I said, like as a data scientist, and give an example for the Coca-Colas, right? And the Pepsis. I don't know what's going on through your brain. I don't know like how do you see your patterns, but I'm making sure that you catch the right patterns.
Because your output is what you
Exactly.
So if your output is what you expected, then the path is fine.
Yes, and if the outcome is not what I expect it to be,
then you got to
then
tweak the.
I do that mathematical operation.
Right,
run.
and then it sets a different path through your 500 neurons, and then when you hit your Coca-Cola, what you wanted,
Yes.
whatever, then you know that path is fine. But,
Exactly.
so once you know your path, is that imprinted? Like, so like if you gave it another image, could you say, do this 500 neuron
Yes.
path, and you should get your outcome?
Exactly.
Ah, that's so cool. Okay.
So that's why there was 2,000 images in total that I inputted, and so it learns. The more it sees, the more it learns. So
when you put your test data and you see it run through and it didn't give you your output, you can go back and say neuron 52 is messed up.
That's for the training data, because the test data, that's for testing. Those are for images you guys never seen before. So
Right.
I don't wanna because if I do that, that's also biased as well.
Ah, I see.
If I do that, so I randomly pick 25% of the images to be testing, and the other ones for the training. So the purpose of training is just that, training.
It's just that, okay.
Exactly.
But at least what confuses me is that you're using the same math, right?
Yeah.
Each neuron sees the same math. If it's the same formula, why each
It's
of
the
them?
brightness, it's your pixel data, I
see.
think.
I'm still trying to
It
capture
uses
this.
the same formula because it's easier to make computation that way, and also all it serves is the neuron chooses one to be active or inactive, and you can add more layers. So there's supercomputers that I use 3 layers only. There's supercomputers that use 10 layers and whatnot, but you want to still be you want to still use the same function, even though this might seem like a simple function. Mathematically, this function can approximate any other function that exists.
No, what Carmen said
But I
makes
think
sense.
your only variable is your pixels.
Is
My only
the
variable
pixels.
is the pixels,
The
yes.
pixels.
Yeah.
Got it.
Are you guys following this?
So,
Okay.
so going back to Julio's
I want to make
question.
sure you guys are following our conversation.
Going back to Julio's question, like you're not just doing one image at a time. Like our one image has what, like 20 Z stacks. I don't know. I'm just making a number. So you're not taking that one image and running it.
No,
You're
I'm
taking like
multiple.
multiple. So can you find a way where you take one image when you're testing? No, what is it called? Not testing, but training. There we go. Thank you. When you're training the computer to, I guess, think, can you take one of those images and all of its stacks and sending it one at a time?
Yeah, so that's
You
what
can-
I did. I grabbed 10 at a time and I sent it to it.
Okay,
'Cause if
but
I do-
in one image though,
Oh,
or
no.
in more.
Like the
I
stack-
guess
you're
like
talking about the
one-
stacks,
No.
right?
What I
One
did
experiment,
basically,
one
what I did
embryo.
was
So you
just-
want like one image with multiple images in it?
So I want. I was thinking one embryo with all of its images.
No.
At a time.
That's if I was to do that, that's also a little biased. So
Gotcha.
I did it randomly. So even though there's a stack with multiple images, I randomized that too.
Okay, and that's where the cleanup comes in. Okay.
So I just treat an image like that, just an image.
Okay.
So can you tell us about the cleanup again? What the
So the cleanup, yeah. So we only took out some images that were like did not show anything, just like straight up black, right? So we just took those out, and also you want to, and this is a point I'm gonna go at the end, but you want to leave room to variation. I'll explain that right now. So, oh yeah, the results. So after training this, our results were this: 93.5 accuracy prediction. So. So what this means
So
basically, what this means right here is,
That's an A.
A, almost an A.
so what this means basically is, this is the how good, no, it's this way. So this is the actual 0 means control. So this is how many of them are actually control, and this is how many of them are actually mutated, and this is the prediction. So it's prediction versus actual. So out of 211 controls, 190 were predicted right. They were predicted as control, but 21 were predicted as mutated. Now, in the mutated ones, out of 320, 307 got predicted as mutated, so you got it right. But 13 got predicted as control. But even though it might seem like, oh, it's not like there's some faulty ones, right? That's still better than most scientists. Like scientists can only predict this by 80% accuracy. So 93%, 93.5 is actually really good. So yeah, I can show you little examples of how this prediction is done. So this is for
How
example.
long did it take you to get there, though? That
Oh.
wasn't the first, like, how?
Oh, but it took a while.
Yeah.
It took a while. It's like testing. It's like trial and error, right? Trial and error. Like sometimes I will get this right here to be like all zeros. It predicts nothing. Or there's things like, oh, it predicts all of them to be controlled, all of them to be mutated. So there's a trial and error. But this was the best fit. This like the last time I run it, I was like, oh, 92% because. So that's the best round I had. Actually, I thought it was 95, but then I ran it again and it went down. So.
So how many runs did you do?
Oh, a lot.
10, 50, 100?
Probably 100.
100.
Probably 100, yes.
And was it incremental? Like every time you ran it, you felt like it got better, or was
It's like-
it you know like you hit a tap, you know?
It's like this right here, right?
Okay.
So it's like this equation right here. Let me go back to the slide. That's better. So right here.
Yeah.
So you're trying to hit the lowest point, right? But sometimes you might go backwards too much that you get to this point. And also another problem with this is that since there's multiple dimensions, you might go to this point right here. And when you're here, you might think that there's nothing lower than that, but there's also things that are lower. So you need to be careful, like making small jumps, little jumps, and that's part of the training process that
And you can go back, like if you did something and you realize I'm going in the wrong direction,
Yes.
you can go back a couple of cycles and then go from
Yeah, that's why you save it and you restore
Save
it.
it and restore, okay.
Exactly. So that's something I did. That's something I did. So yeah, this is some of the images that I saw. So basically, this is in grayscale. So that, for example, control. Those are control, and these are mutated. So I just started an image, and this is just actually, and this is for the testing. So these are not images for training. These are the ones you have never seen before. And you try to the program will tell you right here, predicted, mutated, predicted, control. And yes, so this is a little example of how this thing, like if you were in your lab and you were to throw this image to this neural network, this is how this thing will be visualized.
So all the images that you were given, were they 2-cell injections or 1-cell injections?
A lot of them were 1 cell.
Okay.
I'm sorry, no, 2-cell injections.
2-cell injections, because it was looking at the, so do you know what the difference between 1-cell and 2-cell injections are?
No idea.
No. Okay, so let me just tell you, because that might have made it kind of challenging for you. So if we disrupt a gene of interest at the 1-cell stage, that's right when the egg was fertilized, then we disrupt muscle formation throughout the entire body of the embryo. But if we do an injection to disrupt gene expression at the 2-cell stage, one of those cells is the left side, one of those cells is on the right side.
Okay.
So some of the images you got was half normal and half abnormal.
Okay.
So then how does your machine learning distinguish when half is normal and half is abnormal?
Well, if it says a mutation, so if there's no mutation at all, this is just the control. If it's one type of mutation, then it's mutated.
So for
That's
example, your predicted control there, your machine said it's a control.
Yes.
And on the right side, it looks pretty good. On the left side, it's looking somewhat abnormal. But that was tricky because the most of what it saw was probably normal.
Yeah, no, it's basically because I was given this image as control. So
Yeah.
that's how I train it to be. It's like
See?
Reinforcement, or it's like basically me showing you, okay, this is a Coca-Cola.
So that was a control. So you already knew it was control.
Yes.
Yeah.
I see, because I'm like looking at it, I'm like, my machine is like,
So the ones that, so maybe you'll show
No,
the
it
ones
doesn't
that,
look normal.
Yeah.
The left side right
yeah, are you gonna show her the ones that kind of got wrong?
Oh, no, I didn't put in the presentation.
Okay.
What else?
So I think some that, the ones that got wrong, I wanted to go back to them. I think that was part of the.
I can show you after.
Later, yeah.
Yeah.
So I think some were mislabeled. Me, probably. So when I put them in there, some were probably damaged. So the injection sometimes could damage the soma formation, for instance. So I think one thing that we discussed, going back to your previous slide, the ones, you had 21 or 13 that just were not predicted correctly. We wanted to revisit and see what was wrong with them, because the ones that we talked about, like I gave him one embryo that was way too early, like 24, 23, and even though it was a control, the machine learning, the machine said, this is mutant. Because the vast majority of the other embryos were at stage older.
And so I had to learn what a
Yeah, so I feel like
there's the thing though. Even though this, like, okay, you might try to explain why did they get it wrong. This is actually really normal for this type of programs. They are never perfect.
Well, and it's great because, looking at 21 is a lot easier than 190, right? So you can go back and revisit, right? And then say, oh, okay, well, either we made the error or the machine made the error, right?
No, the thing about it is that you want to also leave room for variation, right? Because, for example, if I show you always the same of a kind, like, and going back to the example of the Coca-Colas and Pepsis, and it's like last time we were discussing like cleaning them up, and showing like better embryos, like good looking embryos, right?
Like the perfect one.
Perfect ones. The problem with that is that, for example, the good Coca-Colas will always be red, right? So if you throw those images only, it will probably not capture what is really going on. It might capture you certain things. So if you throw images, even if they're distorted or anything, that leaves room to variation. And the good thing about it is that it starts to learn. There's things that us cannot catch, but the computer can learn to catch. So it's probably not a problem with the development. Maybe in the development, this thing might also see that, okay, this is good, this is not, right? But the more images that this gets, the better it gets at predicting.
So if we give it a bunch of young embryos, so that was your point, that some of the tests were, then it'll learn both what's normal in a young embryo
Exactly.
as well as what's normal in an old embryo.
Yeah,
Even
that's
though
what I
those
think.
two images look very different, it's gonna learn that both those variations are normal.
Exactly. So it'll learn the patterns
Yes.
behind it. So that's something we cannot see, but the computer can see.
Oh, that's
Do you think to increase its like efficiency in learning, do you think adding more neurons, or what are they called, like levels? Do you think layers? Do you think
Maybe not. I think that this is good enough, because 3 layers is usually good enough. Plus you have 500, so
yeah.
that's a lot already. It might not. Sometimes when I say it might not, it's because, for example, there's a problem in computer science and statistics that's called overfitting. So when you overfit something, so you have your data, right? Like this. A good prediction will be like this, right? And there are some errors. This is not perfect, but it's good enough. But if you overfit something, like say like we want to throw a polynomial equation, this equation will be like, right? But there's a problem with this. I mean, there's 0 error here, but the problem with having 0 error is that, like, imagine there's a data point here. This equation will go all the way down, right? So that's a problem with overfitting, that it might seem like it's the best equation, but it's just fit with that data. And that's something that I want to get to this after, is the next steps, is the increased number of images for training, ensure reproducibility. So imagine that you guys are working with a microscope right now, but then later you get a new microscope, right? You get a new microscope, so the images, the quality, or the way you take the pictures might change, right? And if this thing is overfitted just to look at that kind of data, then it might not work well with different kind of data. So the thing is that we need to ensure reproducibility. So if it works here, we want to make sure that it works in different images as well. Not only.
Along those lines, the images you got, were they all integrant? Was it just one label?
It was a combination of interseminated boundaries.
No, but what were the markers?
There was beta dystroglycan, beta integrin,
Oh, okay.
laminin 12-101. So it didn't care.
Oh, that's great.
As long as you had, that was something we discussed. So
Because the images you got, there was variation in the signals,
yeah,
right? So then, in essence, it got trained using
Yeah, I
all
know,
of
that's-
the different parameters that the lab typically uses.
that's the part that I'm excited about. Because
Wow.
it learned very quickly, and it got. I mean, that's a high percentage to me. That 93 with what I threw at you, basically.
So, and did you throw it?
So
throw
what
it
I
at them as like different files
so
for
the
training, or is it all like
so the
composites?
No, just stacks, C-stacks.
Yeah, but composite signals, like did it show 12-101 and integrin all together, or was it
Right.
integrin by itself, or?
Right, there were 2 channels.
Two channels,
sometimes
so he was
3
working with
channels.
both channels all the time? They were both, is that right?
I was just working with the images. I don't know.
Yeah.
So Julio really knows.
Yeah. The thing, Carmen, is that sometimes, you don't have to know this, but the DMSO gets rid of that red channel, so
Oh,
it didn't
it's-
have it,
it
right?
Didn't have, yeah.
So,
No, it's
but
just good,
what
because now I realized he had a variety of images and
Yeah.
signals. It wasn't like we only used
Yeah.
integrin or something, so.
yeah. So one thing we didn't give you is the small Z-stacks. So way back, before I joined the lab, we used to do a lot of small Z-stacks. You remember?
Are they really thin 1 micron CSAC?
No, just, instead of doing the tile scan, so what I gave him is just tile scans. So whole mount, basically, a whole embryo, but what I wanted to see is, I need to find him, the old C-stacks. So the machine doesn't care if it's just a partial area of the embryo or not. So that's why I think we can add more images.
Okay.
Yeah, and I purposely didn't give you things that were misleading. So I knew what we had predicted. These guys were mild mutant or strong mutants or controls.
I see.
So, but I think going back to the STF, CXCR4, none of those are here. So it'd be really cool to throw, or even or even Moosehut 1 or whatever Brenda has. So
We have
nice to
different
throw.
mutants, so that would be good.
Actually, I got files with different mutations, but the only problem with them is that they were like, some of them were like 200 images, or they weren't that big. So initially I wanted to make 4 classifications: control, mutation 1, mutation 2, mutation 3. But since this is the problem with this, if you want to work with machine learning, you need at least 1,000 images for training. At least, and that's the thing, because I could have done that, but there would not be guaranteed that it actually captured that. So I just decided to put all the 3 mutations that I was given into one single folder of mutations. So yeah. So also, one thing is that I wanted to, for next steps also, fit with flip images. So if I show you, I don't know, again, the Coca-Cola, or I show you the Blake sleeve here, this thing right here. If I was to flip it, you still be able to recognize that this is like Blake right here, right? So that's something for next steps. Like send the images and also the flip images, because some of the mutations were only one side, right? So maybe this thing is getting it wrong. Maybe it's saying, oh, I don't see any kind of light here. So this is just it says, oh, it's mutated, right? But we don't want that. We actually want to see that it gets the mutation, right? That's why for next steps, might have to flip some images.
So physically flip them.
Yeah. So so it's just like just give me the image, and I will throw that image and the same image flipped. So it's
You'll
like
do it horizontal versus vertical.
Exactly. So if I flip it one and twice, I could increase the data set for 3 times.
Yeah, that's smart.
So one thing that we met with Ilmi last week, right? And one thing that she wanted us to do is clean, or what was the term that she used?
You clean the data.
Clean the data a little bit more.
That's where I differ with her a little bit. Me personally, and that's because in Gladstone Institute, they're working with this kind of stuff, and they say cleaning data, that's the problem. You get to be overfitted, right? So you want to leave room for variation. That's the key right there. Leave room for variation, because if you were to clean the data, there's things that for example, if I want to recognize a human, right? For example, take pictures of me. If I show you pictures of me like are just like in front, I want you to also be recognize me if I'm like on this side right here, right? Or like on the back or whatnot. So even though pictures might not be clean, there's still data, and more data is always important.
So Carmen, one thing that so far you cannot do, right, is for instance determine if a cell is individual cells are rotated, not rotated.
It's looking at the
It's
whole
looking at the
embryo.
whole thing. So how would you accomplish this again? Just looking at
there's algorithms.
single somites or single cells, or is that something possible?
There's algorithms out there. There's other programs by other people that can like cluster things, and that would be also for next steps. Make use of someone else's program that is able to cluster like sections of an image, and then out of those sections we can throw it to the same neural network and be able to make better predictions. But those are for next steps, because if you think about it, that separating things or whatnot, that's a total different layer of investigation, and that's not So I would have loved to do that, but that's something like completely different. That's not. I guess it's AI. there's people that don't use AI to do that, but that's something else. So to integrate that with this thing. So yes. Wait. Okay. So well, acknowledgements. Patrick Wang. This is the person I work with during that was my partner in this project. He helped me a lot, especially with the Photoshop. He did not know much about AI, but he knew a lot about Photoshop, so that helped.
Was he in Ilmi's lab?
He was in my class. He was in my class. We worked on different projects before, and he was always my.
Oh, I met him, right?
Yeah.
Yeah, that's right. That's right.
This was the class you took with Ilmi?
Yes.
Was it part of the PINK program?
No.
No.
It was artificial intelligence class. So yes. So Hassan Sami, that's my advisor from Cluster Institute. He was the one that recommended me to use the TensorFlow as well, and he recommended me to use certain tools. So also Ilmi Yoon for teaching the artificial intelligence class. The artificial intelligence class, you don't really learn to do this, but it just shows you like what is in artificial intelligence, because it's a really big branch of it's a really big branch of computer science. So I just chose that one, and we barely went into it, but I had to do a lot of investigation by myself to do this project. And we're gonna meet it for giving me the data.
And the Domingo lab.
Wow.
Because there's so many files from
Ancient
many
history.
people.
Ancient
Rebecca. Yeah,
Rebecca's
it's just, yeah.
That's so exciting. So like once you have this set up, let's say, for example, Colleen is doing cross sections. They're different, you know, it's cross sections. And can she just say, okay, you've set it up, she can just drag her images into your network?
Yeah,
and then is it a matter when it's training it?
No,
just a matter of saying yes
you
or
don't
no?
have to, once it's trained, you don't have to train it again.
Okay.
Unless you have another 2,000 images. Another 1,000 images that you might so say that today you're like, okay, I want to improve the accuracy, so I'll just throw 1,000 images more. So just if you want to do that, cool, like you can train it, but you don't need to train it again. Once it's trained, you can just throw the
But if the images are different, like
yeah.
it's trained now for the whole embryo, like you trained it, it understands the whole embryo for particular stages. But let's say now she does cross sections. Those images look totally different from the ones that you've been
Okay, so
imaging.
if we wanted to learn from cross sections, then you have to have like at least like let's say 500 images of cross sections, like already labeled, and throw it to the training data, train it, and then later like in like the years after your investigation, you get a new image, and you want to see. You don't want to have the time to analyze it by yourself. You just write to the computer, and the computer will just do it for you, given that it's already trained.
So you would at least need like 1,000 images to train.
Yes.
And then train? Yeah. And then, or to learn, and then like you give it 1,000 more images like that are brand new that it hasn't.
Just throw one image. I mean, the purpose
Oh,
for
you can
testing,
throw one, like one stat.
No, for training you need a lot, but for
Okay.
testing you need anything.
So I think you're doing this in the medical field, right? Looking at breast tissue for tumors or abnormal growth, right? Is that how,
Yes,
is everybody
yes.
using that?
In Glasgow Institute, they're actually using this for calculating cell fate. So they show it a neuron cell right there, and it's able to tell how many months it's gonna die, and based on data, right? So they took the picture, they measure how long after taking the picture it died, right? So you just throw that to the neuron and to the neural network, and it's able to calculate the cell fate, right? But you have to be really specific with your data, with your how much numbers you're putting in, right? For example, in this case, I was only given two things, that is control and is mutated, right? But if you give me other numbers, such as someone mentioned fluorescence, right? Then if you give me a specific number, because this is all numbers, so you give me a specific number, specific labels, then I might be able to train it to calculate whatever you want, but you need to have pre-labeled data, you know?
So when you say specific number, do you mean in that pixel, like say that it has fluorescence, that one pixel is 255 and everything else, if it's darker or lighter?
Yeah.
Okay.
Something like that. It doesn't
Okay.
have to go to scale 255, it could be any number.
Okay.
As long as all the numbers are like scale, for example, it's like, if I show you images for cats and dogs, right? I want all the cats to have the label cat. I want to be really
Gotcha.
specific about it. Same thing for the dogs, you know? Because if you throw me images that are not labeled, then I cannot work with it because
Then you don't know.
Exactly. So, questions?
So I'm still kind of confused about, because so the embryos, as they, if you're looking at an embryo, when you do cross sections, for instance, the anterior region of the embryo looks very different than the tail or the mid trunk. All right. So how does the machine know that this is not a mutant? This is all wild type. This is all normal. How do you?
Because it gets 1,000 images of each. It gets 1,000 heads, 1,000 trunks, 1,000 tails.
But you have to pre-label it before you. This is a head. This is the head region.
You don't need to pre-label that it's a head. You just need to just say that there's a mutation here, but there's no mutation here. That's all you need. That's pretty much all you need. Because as I'm saying, like we don't know what kind of patterns is it looking, but as long as we fit in the right data, it will think and will say, oh, there's just a pattern or whatnot, right? So for example, when you listen to music, right? You're listening to your favorite song because you hear a certain pattern in the music. You don't need to know about the frequencies. You don't need to be really complex about what you're listening, but because you don't know anything about frequencies, you don't know about the numbers, but you do recognize the patterns in the music. So that's why you're able to say, oh, that's this band. Oh, this is other music, right? You don't know how your brain works, but you're able to use it. So this is how these things are done as well. It's more like in Google, in many places they call it like a black box. We don't really know what's going on inside. We don't really know the connections between the neurons that are happening, but we know that we're going to the right direction because we're showing it the right data. That's what's happening.
Cool. I mean, it's kind of like, when you get a new student and you show them something, they don't know if it's normal or mutant. They look at it and they're like, what is that? So you go, that one's normal. And then you show it again and you go, that one is normal. And then you do it again and then eventually like, what's wrong with that one? Oh, that one's not normal. But I think it's the same thing. The first time you look at something you don't know, but you just...
Yeah, Celine and I you asked me last night, right? How do you know this is the PSM? How do you know this is...
Yeah.
This
So
is
you gotta
not
train
segmented.
it.
You get trained, but you're training, not a machine, a person.
But you can train the machine to see the nuances though, like
Exactly.
this cell
The
looks like
machine
this.
is dumb though, because it needs 1,000, right? No,
Yeah,
it
that's
is
true.
dumb
A
because,
human
right?
can learn like only with 10 images.
Exactly.
Yeah,
you
okay.
know?
Like thousands of images.
So you need 1,000. So,
Okay.
but I bet you over time that may change. I don't know. Like, maybe there'll be things that, I saw a hackathon, and the winner was a robot that was being trained to identify a thief. It was kind of funny. And so the idea would be that you'd have these robots in stores and you would program it people who had maybe stolen stuff in the past. And so, which is kind of scary because I'm like, God, you really want to make sure that machine is smart, otherwise it's going to identify the wrong person as a thief. But the problem they had was the number of images they had to feed the system within the 24 hours of the hackathon. So,
There's the whole thing called, if they had, for example, this neural network, I pretty much built it from scratch. Like, not entirely from scratch, but I used the software that I was able to do it from scratch without doing that much math. But there is people that use pre-trained models. For example, this is I already trained it, right? There's pre-trained models that online already that
have facial recognition.
Yes, they can like recognize faces. They can recognize things like your ethnicity. They can recognize things like sex. They can recognize things like this is a tree, this is a car, this is this. They are already trained. For example, then those things have like 10 layers.
And so you just need to tweak it a little bit more to get the specificity
Exactly.
that you
So
need.
if I draw a new image, right, then I just have to add a new layer just for training that last layer, right? But this.
So it might
these
not
things
take
are
1,000 images. In that case,
Exactly.
maybe you can only use 50 and you can get it to where you need it to be. Because it was like pre-trained, it was primed.
Yes. So it has already like some like, for example, it's some that look at cats and whatnot, and for the cats it looks at the shapes, looks at tails, right? It's able to like differentiate things. But these things are, I would say, they're smarter, but the only problem with this is that since it's already pre-trained with something, sometimes it's a good idea to throw it this kind of investigation, but sometimes it's not. Sometimes it just doesn't work. So there's that kind of trait. Meaning that it's pre-trained doesn't mean that it's good. It's gonna be good for.
So like you decided to make this from scratch. Was
Yes.
there any reason to use what you had in Gladstone and retrain that instead?
No. I could have. I mean, I could have done that, but if I want to use some, I would have to talk to someone.
Right.
The thing
And
is that
negotiate and all that.
exactly,
Okay.
exactly. So,
Yeah, it's kind of what I had a question for you. Who owns this? Like, is this yours?
Yeah. So-
This is you can patent
yes,
this thing.
basically, yeah. So, I mean, I'm paying for the server. I did all for myself, so I would say like.
You
yeah,
own it.
I own it. No.
Yeah.
There you go.
Sell it.
Exciting.
Yes.
Good job.